In this video, we're going to continue our discussion about httr and rvest by talking about networking and the internet. To start, a basic understanding of how computers communicate is really foundational to modern statistical practice, especially when it goes under the moniker of data science. Most data nowadays is communicated via computer networks, especially the internet and the World Wide Web. Connecting to databases requires a basic understanding of networks, or at least it helps a lot to understand how the underlying network plumbing is working when you're connecting to databases. Moreover, the internet itself contains a lot of information just in itself, in terms of social networks, Internet of Things, and so on. Nowadays, all kinds of devices, from watches to doorbells, are actually on the internet and are sending information across computer networks. So it helps a lot to know how to access that kind of information. When you're learning computer networks, I think the easiest way to start is to try to think about how things developed from a historical perspective. So in our discussion, we'll kind of go back a little bit to some really old technologies, and we'll kind of build things up from there. And it'll give you a contextual perspective on why things are the way things are. In theory, computer networking is really the domain of computer science. But in practice, actual enterprise networks are maintained by IT networking professionals. These people usually have certifications in information technology, but they may also have degrees in management and information systems. It's IT departments that actually create and maintain computer networks. They create users, they give them privileges, and so on. So one useful analogy is an IT department is to data scientists as lab/facilities managers are to actual physical scientists. They're absolutely required to actually get things done. So let's go ahead and get into networking. We'll start with hubs. The oldest computers communicated via Ethernet hubs. They looked something like this, or in a little bit more modern version, now something like this. You might have seen something like this, but it's probably a switch, and we'll talk about switches in just a little bit. We'll diagram these by looking something like this. So it's a little box, and it has 4 of these little ports on them. The ports are usually referred to as interfaces, and the interfaces have these big telephone connectors called RJ45 connectors that actually plug into them. I'm sure you've seen them. At a basic level, hubs are repeaters. So any information that was sent through one interface, through one port, is repeated through each of the others. Now, to understand how this works, you have to appreciate that every computer is actually created with a unique physical address called a MAC address, MAC. This is actually not associated with the computer itself, it's associated with the networking card on the computer, but we'll just say computer for the time being. MAC addresses are 6 bytes long, i.e. 12 hexadecimal digits, and they look something like this on the right. Each byte is distinguished by colons, so the colons are not actually part of the MAC address there. They're just to help us read it. Now, the first 6 hexadecimal digits are actually unique to the manufacturer, in this case, Apple. So if you see those first digits, you can actually tell who the manufacturer was, and that'll tell you some information about the actual physical device that the user is using. Since writing 12 hexadecimal digits is kind of long, and since the first 6 digits are unique to the manufacturer, not the device, I'm only going to display the last 6. So diagrammatically, the setup would look something like this. You have 4 different computers, they're each plugged into a hub, they're each identified by their unique MAC addresses, okay? So here on the left, I have the computer F09F3C, and let's say that it wants to communicate with the computer DF62F0 right here. So let's think about how that communication would work. The first computer addresses the information it wants to send out to the MAC address of the second computer. The hub receives that, and the hub, as a repeater, just repeats that information to each of the different computers on the network. The first computer sees it and says, well, this is not intended for my MAC address, it's not intended for me, so I'm just going to discard it. The second sees it and says, this is destined for me, I can open it up, and the third says, this is not for me, I'm going to discard it. So that's how this would work. Now, there is a unique MAC address that refers to broadcast. So if the first computer wants to refer to everybody on the network, it can just send the message to the MAC address of all Fs, and all will then receive it. Now, the collection of all devices on a network that are able to hear a broadcast is referred to as a broadcast domain. As a simplification, these are about the same as local area networks. There's a little bit of a difference, but it'll get you by. And hopefully you can tell just by seeing this that hubs have some pretty serious limitations. First of all, there are security concerns. You have to actually trust the other computers on the network to actually throw away the information that's being sent to them. That may not be a big deal on a small network that's just your computer and a printer, but in bigger networks it is a big problem. Secondly, they don't scale very well. As the number of computers on the network increases, the ability to communicate significantly decreases because everybody is sending these kind of broadcasts all the time. So there's a lot of people that are just kind of talking on the network. And that's why it's actually very rare to find hubs these days. Nowadays, we usually use what's called switches. Switches can look like the blue box that we saw before that was a hub. The switches may look absolutely identical, but larger enterprise switches look something like this. They've got tons of ports on them. Switches are distinguished from hubs by the fact that they keep a table that pairs together MAC addresses plugged into each of the interfaces in the interface itself. In other words, switches aren't dumb repeaters. Switches are smart. They know exactly which MAC address is connected to which interface. Now, some switches are actually smarter than others. Some switches are called managed switches. These switches actually have operating systems in them that govern their behavior. So you can do things like break up one switch virtually into several different switches. More commonly on the user side, you encounter unmanaged switches. Unmanaged switches are very much like the hubs that we were talking about before. The only difference is that now they send targeted messages out. And this is what that looks like. You'll have the switch. Notice that on the switch, it has actually labeled the MAC addresses of the devices that are actually plugged into each of those interfaces. So it knows who's on each line. Now suppose we wanted the same communication to happen that we referred to before. The computer F0 wants to communicate with the computer DF. Okay? So it goes ahead and it sends out a message to that particular MAC address. The switch receives that and says, okay, well, I know DF is on this interface, so I'm only going to send it out that particular interface. I'm not going to send it out the others. So there's no possibility that devices that are connected to other interfaces will actually see that information. As a nice added bonus to this, switches can also manage traffic that's going across different interfaces simultaneously. So if the other two computers wanted to talk at the same time, they can do that, and there's not really an appreciable hit to the speed there unless there's a whole lot of that going on. And that will somewhat depend on the quality of the switch. Switches, of course, also can support broadcast. So if the computer F0 sends out a message with all Fs, each other device on the network is going to actually receive that. So at a basic level, switches are better than hubs, but they too still have limitations. As the broadcast domain grows too large, in other words, as too many devices are still in that same broadcast domain, the network can still get swamped by broadcast. And broadcast will happen, for example, when any computer joins the network. So if you plug anything into the network, it's going to start broadcasting out to everybody else on the network. Obviously, if you have a lot of devices on the network, that kind of thing could happen a lot and start swamping the network. Before moving on to the next step, it'll help to know what data communicated across the wire actually looks like. As a simplification, data is sent in what's called an Ethernet frame. And an Ethernet frame can have a payload, or the kind of amount of information that's hauling, of 1500 bytes at maximum. The diagram here is really helpful. You have the computer that's sending the information on your left. That's your F0 computer. This is the frame itself. So it's, as far as the computer is concerned, it's just a sequence of bits. That sequence of bits begins with some header information, which is essentially just saying some stuff about the frame. The destination MAC address, this is where the frame is intended to go. The source MAC address, that's who's sending it, so that the recipient of that can turn around and send information back to the original sender. Then it has the payload, that's the actual information it's hauling across the wire. And last, it has a frame check. This is some information that's actually just attempting to make sure that the information that was sent across is in fact the correct information, so that there weren't any physical anomalies, for example, that degraded the signal in going from point A to point B. It's your network's job to actually chop up data, i.e. files and so on, that you want to send. So usually you want to send things, of course, that are significantly larger than 1500 bytes. Nevertheless, to go across the network, they've got to get chopped up. Your network card is what actually does that chopping. So those are Ethernet frames. To make networks larger, you actually need what's called routers. Routers interconnect broadcast domains, but broadcasts don't themselves go through routers. That's the main distinguishing feature that's going to save you from that really loud noise that's coming from a large network. At a basic level, routers are going to look a lot like switches in the sense that they're going to have Ethernet ports on them where you plug in cables. The difference here is that every interface is itself going to have a MAC address. So routers don't just have one MAC address, they have many MAC addresses, one for each interface. So the diagram would look something like this. I've got two broadcast domains, one in green, one in blue. They each have several different devices that are connected to them, several different computers. Each one of those has its own MAC address, and then they're connected to the router. Notice that on the router, each port, each interface has its own MAC address. And the corresponding interfaces on the switch know those MAC addresses. In other words, as far as the switch is concerned, the router is just a different computer. It doesn't really know the difference. And as a consequence, each of the computers on each of these networks, on each of the broadcast domains, can send information to the router as if it is actually another computer on the network. Now you may say, well, how does that really help things? And to understand that, you need to know something about logical addressing. Routers assigned different kinds of addresses to each device on the network that are referred to as logical addresses. These addresses are different than the physical addresses that the computers are actually made with. These logical addresses are assigned typically via a process called DHCP, or the Dynamic Host Configuration Protocol. This is an oversimplification of things, but this is certainly true at the lower levels of the internet. And at the higher levels of the internet, a whole bunch of different stuff is going on that we can abstract away. It's not really going to matter for our purposes. So these IP addresses are going to be assigned to each of the devices on the network, and they're going to be in addition to the physical MAC addresses that they have. So each device is going to have one physical MAC address and typically one IP address, although in some cases you may have many IP addresses. For most users, as I said before, IP addresses are ephemeral. They're dynamic. You'll have an IP address for a particular period of time, and then your IP address will change. Of course, as a user, you'll never really see this unless you're working with networking things, and then you'll notice that your IP address changes. So again, for the user level, your IP address is usually changing very frequently. However, at a higher level of the internet, even at the level, say, of your house, your IP address is more or less static, and the higher you go in the internet, the more static it's going to be. The ranges of IP addresses are actually set up when the network is created by the network administrator. So whoever kind of puts the network together with the router and so on, they're going to actually create the ranges of IP addresses at the very beginning. So this would be something like a developer is going to create a new neighborhood. They're going to name all the streets in the neighborhood. And then the individual houses are going to get individual house numbers just depending on kind of like where they are on the street. In this video, I'll just talk about what's called IPv4, or Internet Protocol version 4 addresses. These addresses are all 32 bits long, or 4 bytes long. Bytes in this context are often referred to as octets. It's very common to refer to IPv4 addresses using what's called dot decimal notation. So these 32 bits, or 4 bytes, can be associated together in a grouping of 4 different numbers that are each between 0 and 255. Those are the decimal values of the hexadecimal digits that constitute each of the bytes. So at least as far as we're concerned, IP addresses will always look something like 192.168.0.1 or 127.0.0.1. Something like that. Every one of the digits is always between 0 and 255, and there's always 4 of them. There's never an exception to that. Moreover, the order of those digits matters a lot, not only their values. All devices on the same broadcast domain have the same first numbers. Now, the number of numbers that they have in common may vary, and this is where things get much more complicated with things like subnetting. But for our purposes, you can just think about it like this. The first sets of numbers, however many that may be, is going to define a network ID, and anybody else who's on your network is going to have the same first collection of numbers. For example, at your house, probably everybody is on a network that starts with 192.168.something.something. And that's just the default mode. That's the way things are usually set up. Firewalls are hardware or software that filters internet traffic based on the source IP address. It can also filter based on ports, so we'll talk about that in just a little bit. But at this point, you can just think, we have routers. Routers are communicating information based on IP addresses, and firewalls are going to be either software or hardware that's actually going to disallow that kind of traffic from moving around just based on kind of like where it's being sent from. Okay, so let's go back to our diagram. Our diagram now looks something like this. We have our router, we have our switches, we have our devices on their networks. Each of those we know has a MAC address, but now the router is assigning to different devices on the network IP addresses on top of their MAC addresses. And for every broadcast domain that we see, it has an IP address that starts with the same number. For example, on the network that's in green, the network ID is 192.168.0. The .1 is referent to the router, and that is almost always the case. That's just the general convention that people use. The router itself has an IP address that terminates in .1. That's just a standard convention. So for example, at your house, I'm bargaining that if you open up a web browser and you type in 192.168.0.1 or 192.168.1.1, you will actually get a web page where you're speaking to your router. Now, going to the green broadcast domain, notice that the first device is 192.168.0.8. The second, 192.168.0.37. The third, 192.168.0.64. Notice the pattern? They're all 192.168.0. something, but the last number is saying which device it is in that local area network. Now, those don't need to be in order. It doesn't have to be 2, 3, 4 or something like that. It can be any number between 1, or in this case 1 is reserved, so 2 and 254. 255 is going to be reserved for something that I'll mention in just a minute. In the purple broadcast domain here, we have 192.168.1, that's its network ID, and then the router is 192.168.1.1, and then every other device gets something else, 192.168.1.4.1.97.1.178. Now, if this is the case, these two broadcast domains can communicate with one another. So a computer that's in the green broadcast domain, for example, the first one over here, 192.168.0.8, can of course speak to this computer over here, 192.168.1.178. The way that it does that is it addresses Ethernet frames to the router that contain information that say that the device it wants to communicate with is actually on the other network, and the router knows how to send that. Consequently, usually what's going to happen here is that one of the ports on the router is actually going to be connected to what's called the wide area network, or in colloquial speak, the cloud, the internet itself. And this is actually usually via the ISP, the internet service provider, or whatever the organization is that's actually providing the connection to the internet. As far as the router is concerned, this is referred to as the internet gateway. And as I said, it's connected to the so-called WAN, or the wide area network. Now, you might have asked yourself, IPv4 addresses, just being 4 numbers, each between 0 and 255, that's a lot of numbers, but it's not that many numbers. It's not as many numbers as you actually have connected to the entire internet, right? I mean, nowadays we have so many devices that are out there, way more than just IPv4 addresses. How is it that we don't run out of IPv4 addresses? The basic idea is that we don't run out of IPv4 addresses because private networks can share one public IP address. For example, all the devices at a particular organization, or all the devices at your house, for example, all share externally the same IP address. But internally, meaning behind the router, they share different IP addresses that are only private IP addresses and only work within your particular house or organization. This happens through a process called Network Address Translation, or NAT. The only reason you need to know about NAT is, first, to know why we don't run out of IPv4 addresses, but secondly, to know that externally, meaning outside of these private networks, it can actually be difficult to communicate with devices that are beyond the network, because you don't know their IP address in advance. They don't have a public-facing IP address that you know about. You only know about the IP address of the router. So speaking to a particular device on the network is actually challenging because you don't know his IP address behind the router. Now, on the subject of private IP addresses, there are actually big blocks of private IP addresses that are not internet routable. The first one is the major one that you meet in an enterprise setting. That's 10.anything. So 10.anything.anything.anything is usually used by big enterprise networks, for example, Baylor's internal network, and anything with a 10.IP address is an internal address. It's not routable on the broader internet. Second, 172.16.anything to 172.31.anything. This is another big block of private IP addresses, but it's a little rare to see these actually used as private IP address ranges. The last is the one that you see all the time because you see this at your house. It's 192.168.anything.anything. Most home networks are set up like this, so when you just buy a router or you get one from your internet service provider and you plug it in, your IP address range is almost always by default 192.168.something.something, and usually 192.168.0 or 192.168.1. And the .1 device on that network will be the router itself. We don't usually think of the next one as a private IP address, but 127.anything is loopback. Loopback is actually a reference to the computer that you are currently on. So your computer in your private network will actually have a different IP address, but if you refer to the device that's 127.anything, that's actually just going to refer back to your own computer. Now, almost always in practice, the way that you actually see this is 127.0.0.1. And when you see it actually referred to by its alias, you'll see it as what's called localhost. So localhost is just an English word that refers back to 127.0.0.1, and that is your own computer. That's yourself. Now, just like you can send broadcasts In the Ethernet level, you can send broadcasts in the IP level as well. It's 255.255.255.255. And that's why you can't have an address that terminates with .255, is because it's already going to be reserved for IP broadcasts. So if you send something out to that address, it goes to everybody on your local area network, everything in your broadcast domain. Now, if traffic through switches goes as frames, IP traffic is going to operate as packets, and those packets are actually nested inside of Ethernet frames. So the diagram previously looked like this. This was when we were just sending information over Ethernet frames. Now, when we're using IP addresses, the IP addresses are going to add another layer, but that other layer is actually going to be nestled inside of the previous layer. So we still have that same device that's on the far left, but now it has an IP address associated with it that's actually given to it by the router at the very beginning. Kind of like when you're plugging it in, they have this little dance where the computer actually gets assigned an IP address. Now, we still have the overall frame, but nestled inside the frame itself is the IP packet. The IP packet has information like the destination IP address and the source IP address for the exact same reason that it has a destination MAC address and a source MAC address. First of all, the IP packet needs to know where it's going. That's what the router really cares about. The router cares about what the destination IP is. The receiving computer cares about what the source IP address is. Because when the receiving computer wants to speak back to the original source, it needs to actually use that, the source IP, as its destination IP. So that's how they're talking back and forth. So now we know about switches, kind of Ethernet, and routers, IP stuff. The next thing that we need to know about is ports. So up until now, we've only talked about ways that one computer can talk to another computer. But that's kind of not enough for ordinary communication. The computers themselves need to know where the information needs to go in the computers themselves. Internally, applications are identified by ports, and ports are simply numbers that are listed between 1 and about 65,000. So there's lots of different ports on your machines, and you could think in some abstract way that each of these is going to refer to an application or program running on your computer. There are two main ways for computers to communicate. They're referred to as protocols. So these are kinds of dances that computers do over the network where, they greet one another, or maybe they don't greet one another at all. The most common way is what's called the Transmission Control Protocol, or TCP. This is a connection-based protocol, which means that the two devices that are communicating to one another are first going to ask each other, are you there? The other computer says yes. Are you ready to start communicating? Yes, and that kind of thing. So there's a connection that's actually being maintained between your two computers. Then the information that's going to be communicated between those two is going to be called segments, so TCP segments. And these are actually ordered, so that when one computer communicates with another, and it has to chop up that information into little pieces. Well, the network itself is not going to ensure that those pieces get there in the same order that the sender actually sent it. But TCP is going to make sure that that happens. So in TCP, each of the segments themselves are going to be ordered so that the recipient knows how to reassemble those in the way that they were sent. Most traffic over the internet is sent through TCP. The main contrast is what's called UDP, and UDP is connectionless, and it's mostly used for telecommunications and network stuff to avoid all of the overhead associated with things like the order of the TCP segments and so on, right? That's got to take up some space within the packet itself. Well, you can send more information more quickly if you just send it. So UDP is a little bit less reliable, but it's more efficient for sending things, and that's why you see things like telecommunications and a lot of low-level network protocols, those are using UDP. Both of these protocols can actually communicate on any port, but most well-known ports have well-known pairings of protocol and port number. So let's look at those now. The first 1024 ports are known as well-known ports. Now, all the ports that I'm going to refer to are going to communicate via the TCP protocol unless I say otherwise. So in networking, when somebody refers to port 80, they're always talking about HTTP traffic. We'll talk about HTTP in the next video when we talk about httr, but right now just think this is how things usually communicate over the World Wide Web. So when you open up a web browser and you go to a website, it's usually communicating via the HTTP protocol over TCP port 80. Nowadays, actually, you see traffic go over port 443, which is HTTPS. That's still web traffic, but the S on the end is indicating that it is secure. So this involves cryptographic protocols so that communications between the two devices, even if they're listened to, will be incomprehensible. Other port pairings are things like port 22 is for SSH. So if you want to log into a remote computer like a server or high performance cluster, this is how you would do that. You would do that through SSH at the terminal. Next, things like SMTP and IMAP. These are protocols for sending email and receiving email. Those happen over ports 25 and 143. So for example, if you were to block these ports, your email wouldn't work anymore. Firewalls, of course, can block data going to particular ports as well, and usually by default is. So firewalls will usually have all of the ports closed, unless for some reason they need to be open. For example, if you're running a web server on your computer, you would want to have port 80 and port 443 open. Next, DNS, the domain name service. We haven't talked about DNS yet, but DNS is going to play a major role in httr next, so it's helpful to kind of refer to it here. It's working over TCP port 53. Then there's things like DHCP. DHCP, remember, that's what the router is using to dynamically assign IP addresses to different devices on the network. That's usually happening over UDP. And it does it over ports 67 and 68, although there are a lot of other ports that could be involved in this. As data scientists, we see ports for applications that are standard, but they're not considered well-known ports. So for example, RStudio Server is going to run over port 8787. So if you have a computer that's hosting an RStudio Server instance, you're going to be talking to that computer over TCP port 8787. If it's a Shiny server, it'll be port 3838, and databases themselves will have unique ports depending on which kind of a database you're referring to. So for example, if it's a MySQL database, you'll be talking to it on port 3306, or MariaDB would be the same way. But different kinds of databases would use different ports there, and they would all be over TCP. So what we've talked about in this video is what's called the TCPIP model for computer networks. It consists of 4 different kind of pieces that we can think of conceptually as creating a computer network. The first is what's called the link layer. That was kind of everything that we talked about with switches and MAC address and Ethernet frames and broadcast domains and local area networks and so on. That's the first layer. The second is the so-called internet layer. When you think about the internet layer, you should be thinking about IP addresses, packets, routers, and that kind of thing. Next is the transport layer. That's TCP segments. It could also be UDP, but you should be thinking it's kind of like the protocol that you're using to talk right before the application level. And that's the fourth layer. The fourth layer is the application layer. You should be thinking things like HTTP or SSH, FTP, the file transfer protocol, but used to just send files across the internet, DNS, and so on. Databases would also be on the application layer. So these are the 4 components of the TCP/IP model. Now, when we add TCP segments into our diagram that we saw previously, now we have an additional part, and the additional part is the TCP segments themselves. So just like we had a destination and source MAC address, we have a destination and source IP address, now we have a destination and source port as well. That's how we talk to the individual ports on the computer, and then for TCP specifically, it's going to have a sequencing number that's immediately going to follow the source port. So for example, if I want to go to Google, I'm going to communicate with Google on HTTPS port 443, but I won't necessarily tell it to respond to me on 443. It will probably respond to me on some arbitrary, large number port like 13,524 or something like that. But whatever it is, I will assign that when it goes out the door so that it knows who to respond to and on what port. Actually, I guess here I've written the port as 5678. Usually we denote these ports preceded by colons following the IP address. So now Google knows, okay, when I write back to David, write back to him on port 5678. And in fact, my router and the firewall in my router probably care about that as well, because routers usually keep track of that so they know kind of like how to filter things out better. As a last side note before we conclude this video, a few notes about home networks I think is just kind of useful to understand kind of what the boxes do around you. So home networks usually consist of 1 or 2 physical devices. If there are 2 physical devices that constitute the network, the first one is usually a modem. A modem is actually going to convert the physical signal that is used to communicate information. So usually that's different voltages across a line or something like that into the actual information that's going to be routed to computers. Okay, so modems are always used like that, whether the information they're receiving is differences in voltages, or maybe it's fiber optic cable, so it's differences in typically laser light or something like that. It's the modem's job to convert physical things into logical things. The other device you would have is actually usually just one box, and it actually combines each of those technologies that I referred to earlier in this video into one box. So it would be a router and a switch and a wireless access point. So a wireless access point, of course, is effectively just going to be a switch that doesn't require Ethernet cables. Now, I should say that the bandwidth of those is significantly lower than devices that are actually plugged in. So plugging your computer physically into a switch is going to be significantly faster than using a wireless access point or just working over Wi-Fi. Nevertheless, from a network perspective, they're connecting to a network in a very, very similar way. So they're still working with MAC addresses and so on. In other words, your wireless network card in your computer has a MAC address, and so does your wireless access point. Now, if your home network has only one device, it's actually usually all of those in one box. So usually you'll have a wire come from your internet service provider, it'll be a coaxial cable, it'll kind of screw into the back of one box, and that one box is going to do everything. So to the end user, it looks very simple, but now we know it's actually significantly more complicated. So that's the basics of how the internet works in TCPIP. Our next video is on HTTP and httr.